So the potential for geothermal in Northern Ireland. And before we get there, I want to talk a little bit about geothermal in general, obviously to talk more specifically about EavorLoop and what the technology offers in terms of making geothermal scalable in a way that it hasn't been before. And with that question in mind, let's look at the context within Europe as a whole. So there are many different geothermal applications, and they really fall into broadly two categories: either power generation or direct use of the heat. Cooling, of course, is a third application, and we're certainly looking at some of those in the Middle East with district cooling networks. But really, the main applications in Europe are heating and power generation. Obviously, Iceland has a long history, and believe it or not, they're actually producing bananas in Iceland. I mean, they're not sold. Iceland is, the popular myth is that Iceland is the EU's greatest exporter of bananas. It's not true, but they do produce bananas, and have been producing bananas in Iceland for a few decades. But Iceland is certainly, its district heating is run on geothermal. Other places where geothermal is being used extensively, obviously you've got the Paris heating network, district heating network, which runs on the Dogger formation. It's a beautiful aquifer. More recently, there have been aquifers found under Munich. So Munich now has a district heating network that is fed by geothermal. Turkey has done a lot with geothermal power production in recent years. But if you look here, if you look at just one simple number, district heating. So there are district heating networks, and I know there aren't many substantial district heating networks in Ireland, but if you go into Germany and you go further east into Poland, I mean, most cities run on centralized district heating systems. Every city in Poland, for example, has a district heating system for cities with more than 10,000 people. And you'd think to yourself, wow, geothermal would be a great application for that type of district heating network. And why not decarbonize all of those district heating networks across Europe? And of course, that should be the case. So why is it that less than 1%, of the heating demand across Europe is supplied by geothermal? Particularly when you go back over time and you look at when the first sort of district heating geothermal applications came about in 1890 in the USA, in Iceland as early as 1950, in 1970 in France, and even though the Munich one may appear to be relatively new, they first started looking at that back in 1990. So why not other sources? And the reason for it is actually pretty simple. If you look at traditional geothermal, even though we're looking for heat, and the center of the Earth is sitting at about 6,000 degrees, and it's going to stay roughly at that temperature for a few billion years. So the heat is there. It's always going to be there, and if we can tap into it, that would be fantastic. The traditional method of tapping into that heat has been to look for underground rivers or aquifers where the water is being heated by the center of the Earth, and where that water can be extracted. So typically you're pumping fluid down through a natural permeable rock formation and producing on the other side. If you find marginal permeability, then you've got the option of fracking. It doesn't necessarily work in Europe, particularly when you're trying to build heating systems underneath cities. So fracking isn't something that is necessarily embraced enthusiastically. And there have been incidents more recently where fracking on the border between Germany and France in Strasbourg, where Fonroche had some challenges with pressuring up a formation to try and create the permeability. So if you can find a geothermal reservoir, it works really well, as I mentioned in Paris and Munich, but it doesn't always exist. And in many ways, finding these geological conditions is like looking at the Earth as a haystack and saying, well, look, I can find this, but I've got to find the needle. Whereas if you can simply build a giant radiator underground, I mean, that is the haystack. If you can find the needle, perfect. If you've got those perfect geological conditions, then that is good. The way we are approaching it is to say, well, the heat is always there, and if we can drill deep enough and we can find the decent temperature gradient, we can build an underground radiator. We can seal it. We can put cold water down here, and once it's warm and comes back up, and the system is fully charged, it actually flows on a thermosiphon. So there's no pump load associated with this whatsoever. So obviously no fracking, because what we're doing is a lot of drilling. No water use, no brine production, and obviously it's baseload, but it's also dispatchable, which means load following, and I'll come on and talk about that. When we first started looking at this a few years ago, everybody said we were mad, and a lot of people still think we're crazy. And they said it'll never work, it doesn't work. The process of extracting heat this way through conduction rather than convection is inefficient, and they're absolutely right. And this is why you need a large surface area to make it work. And then, of course, the next question was, well, that's a lot of drilling. That's too expensive. Even if you can get the heat out of the ground, you won't be able to do it economically. And of course, that's also true. But if you look at what's happened in North America in the shale industry, it used to take 3 months to drill and complete a long-reach horizontal well. That's now drilled and completed within 8 days. So suddenly the economics work. And then people said, well, where have you done it before? And we said, well, we haven't done it before. They said, you need to prove that it's actually going to work. So we set about doing that. We raised some money to do exactly that in Canada. This was the concept. The idea was to have 2 drilling rigs, 2.5 kilometers apart, to drill down, get them to meet in the middle, go back and do the same thing, drill a second lateral. So we found a place to do that just north of Alberta in Canada. It's about an hour and a half north from Calgary, and then about 10, 15 minutes west towards the mountains. And we found a crystalline sandstone down at about 2,500 meters, about 15 meters thick. So that's what we drilled. You could see one drilling rig from the other. We made the second lateral connection on September the 1st, which was a world's first. We then commissioned the system and connected it up, and it's now been running on thermosiphon. So obviously we had a pump to charge the system with fluid, switch that pump off, reopen the valves, and it just has been flowing ever since on a thermosiphon. More importantly, the predicted thermal output has consistently been within 2% of what we predicted. So the measured versus predicted within 2%. How did we predict what it was going to produce? Well, obviously from offset wells, we understood the temperature gradient. And from the offset wells, we could look at the lithology and look at the rock content and estimate what the thermal conductivity would be. We knew what the size of the pipes would be. We had an estimated idea of what the thermosiphon would produce in terms of flow rates. And from that, and our thermodynamic models, we were able to make those calculations. So that's what we did. So we drilled and intersected. The other thing that we were testing was to drill and seal these horizontal sections chemically. So we're not using casing, which makes the thing simpler and far more cost effective. Because the big risk with our operation is less the geology but more so the cost of the drilling operation itself. So we're doing everything we possibly can to reduce the cost of the drilling and completion of these systems. And of course, then the other thing was validating the thermodynamic models. And our models and the data have been independently verified by what now seems like countless organizations, but including TNO, which is the Dutch Geological Survey in the Netherlands. They took all of the raw data, validated our model, did their own modeling to confirm that the thermodynamics were accurate. And of course, we've recently attracted investments from BP and Chevron, who, of course, did their own detailed due diligence into all of the technology, and in particular our thermodynamic models, to convince themselves that what we're talking about does make sense, and the investment was justified. So a couple of things we've also learnt about the technology, and that is its dispatchability. So if you can imagine a 10 megawatt system, this flat green line here, that's going to give you 240 megawatt hours over a 24-hour period. But of course, in the middle of the day, you may have solar, you may have wind that is, fulfilling the demand during the middle of the day. But the great thing about EavorLoop, which again is unique compared with traditional geothermal, you have the ability to vary the flow rates by just choking and unchoking the valve, slowing the flow rates down, and so delivering less heat, more heat during the morning peak, less during the day, and then picking it up again during the heat. Now, the area under the curve is still 240 megawatt hours. You can't change that. But what you can do is you can deliver those 240 megawatt hours in almost any shape you want. So it's a load-following resource. You can think of it more like an earth battery. That's probably the simplest way of thinking about the way the EavorLoop system works. The other thing, after we drilled the project in Canada, then we started to look for our first commercial project, and a lot of the commercial banks that we spoke to said, you've got to prove this technology commercially. Yes, we understand Everlight and it works and everything else, but that was more of a proof of concept. I mean, it's a pretty big proof of concept, but a proof of concept nonetheless. So we've set about looking for our first commercial project. That one looks as though it's going to be in Germany. This is a schematic of the way things will look. So there are two rigs pretty close together on two different well pads. This is what it will look when it's completed, because this is principally a power project with some district heating as well. The district heating network will be built over time. These are what the cooling towers will look like, but once we're completed on surface, everything will be below grade. Configuration, we're going to drill 4 EavorLoop systems, something like that will look like this. And this project came about in Munich. People were looking for an extension of the permeability, the aquifer that they found underneath Munich, and that permeability eventually pinched out till they started to drill dry wells. So what we've done is we've effectively taken over that project, and we'll reuse the well pad and obviously all the knowledge and the data to inform us on how and where to build the EavorLoop systems. So we expect to start drilling either late this year or early next year. And as I said, 4 EavorLoop systems, about 9 megawatts electric, 65 megawatts thermal. Temperature gradient of about 32 degrees per kilometer is what that is. The other question that we often get is, okay, well, at what price can you generate the electricity? Can you generate the heat? And this is a sort of a complex diagram, so let me explain it quickly. You've got two gradients here. an electricity price and a heat price, levelized cost of electricity, or the price needed to generate a 15% return for equity investors. So this is where we are with our technology today. This is where we're heading and where we will be in a few years' time. So if you look more towards this end of the graph, you'll get an idea of, based on power and heat prices in Northern Ireland, whether there are any possibilities. The colors, are based on temperature gradient. So this is the key thing. What is the temperature gradient? We also look at the thermal conductivity of the rock. By the time we get down to this sort of technology, we're not really worrying too much about the sedimentary rock. We're actually building these things in the basement, in the igneous rocks, if possible. And of course, the heat prices then, we're coming down to pretty attractive heat prices. So what we're hoping is, with this technology roadmap and the pricing and the way we believe we can bring the pricing down, is that we can finally make geothermal into a scalable energy resource in a lot of places around the world. Just to look more closely at the cost of heat and how that is changing or likely to change over similar timeframes, because if you can find applications for heat, it is obviously far more energy efficient. If you can take heat out of the ground through a heat exchanger, use it as heat, that's a 90% energy conversion. If you're going to produce electricity, you're talking about 15, 16% energy efficiency. So heating, when you're looking at geothermal, you've always got to look at potential heat applications first before you think about power generation. So very quickly onto Northern Ireland, and there are a number of different ways of looking at the geothermal energy potential. This paper here was a paper submitted for the World Geothermal Congress in Bali, talking about the geothermal energy potential in Northern Ireland. I would really encourage you to go. If you haven't already read that paper, I'd really encourage you to read it. I think it's a really good summary of what the geothermal energy potential is in Northern Ireland. So it has a lot of data from individual wells. It also talks about the megawatt potential of the different reservoirs that were identified in the report. You've also got other sort of indirect references to temperature gradient through the Curry point. So there's a decent hotspot which sits on Northern Ireland. So this plus the well data would suggest there are temperature gradients anywhere between 20 and 38 degrees per kilometer, or perhaps even higher. And obviously here some suggested hotspots as well. Potential applications for EavorLoop itself. Ideally, we're looking for projects of at least 10 megawatts. If we're going to get into district heating, then really cities with at least 30,000 people. Combined heat and power, different story. Maybe 2 or 3 EavorLoops would work. And then on the agricultural and industrial side, we're looking for demand of about 50 megawatts. So those are really big in agricultural or industrial applications, which we would be more than happy to look at and consider in Northern Ireland. Each EavorLoop provides enough heat for about 11,000 homes on average, or enough power for 5,000 homes. So that'll give you a scale of the types of projects that we're looking for. If you've got small individual dwellings, then of course you've got the possibility of using ground source heat pumps. So our focus really is on the bigger projects. So for power, as I said, more than 5,000 homes, or for heating, upwards of populations of 30,000 people. The projects that we're really interested in, though, on the power side, are really large-scale, gigawatt-scale projects. And why is that? If you think about what we're doing, the scale of the drilling, we want to turn this into a large-scale manufacturing operation where we just drill in exactly the same place over and over and over again, where we're drilling maybe 10 or 12 EavorLoops on each well pad, about the size of a football pitch, and then moving across and doing that over and over and over again. And in doing that, then you get the economies of scale. You could have drilling rigs sitting in the same place doing exactly the same thing for years at a time to build up in increments of 3 to 7 megawatts. Each time you finish one, you put that on the grid, you move across and you do the next one. Or if you want to think about building district heating networks in cities like Belfast, then you need to think obviously long time, because you've got to build the heat network and you've got to think about the heat source. But is that a viable option for decarbonizing heating networks in cities? We certainly think so. Our focus currently, of course, is on cities where the district heating network already exists, and there are plans to replace the coal-fired power plant that feeds them. So in Berlin, where I am based now, we're looking at 6 potential projects. We have a project in Hanover. We have numerous projects in other parts of Germany in the pipeline. We've also started to look at our first district heating project in Poland as well. Of course, we're also still looking to get our first commercial project in the ground, and our criteria there are really simple. It's all about speed, and where can we get it in the ground before the end of next year. So that is pretty much all I was going to cover, and as I said, I wanted to leave plenty of time for questions.